Right, good morning everyone. I'm glad to be here. My name is Yousry. Have been working with Spark for the last 6-7 years, and I'm here to show you a few pitfalls and best practices on how to use Spark in your data pipelines. But I think we got an initial quick show of hands. How many is using Spark? Okay, yeah, good enough. So if you don't even use it, using stuff like BigQuery, Snowflake, or whatever, you'll still get some value, some ideas, all right? And let's get started. All right, so what you will learn from this session, a few things. One of them is to improve your pipelines. So it's not even about your developer experience being lovely and quick with Spark. It's also about your production pipelines and making them fast, because that will translate into money. Second thing for sure is how to improve the Spark app such that they will follow best practices, they will be maintainable. And for sure, a bunch of ideas here will be around big data and distributed computing in general, not really tied to the Spark ecosystem itself. And eventually we'll learn a few extra buzzwords. So agenda here is measure 3 parts. First one is Spark anatomy and how that will impact your pipelines or applications. Oops, sorry. Second one is certain query patterns and how that relates to how your application will run. And the last one is a group of miscellaneous items. So quickly, Spark is kind of the Swiss Army knife for your data pipelines nowadays. You have seen the slides from Mickey, and you remember that slide was thousands of tools. So the idea is that it will be very hard to learn many tools, but it will be somehow manageable to learn a single tool to do many things. So Spark can be used for exploratory data analysis, machine learning, building data pipelines, and many other things, okay? And you can find it on many platforms, on the cloud, locally, Docker, even in very old Hadoop environments, okay? So you'll find it everywhere. So let's talk about Spark anatomy first. So Spark is a driver and a group of executors, okay? So the driver is just for orchestration. Don't use it to pull data and deal with it like as if it is pandas. That will not work, okay? In many cases, people consider the driver or run code and then collect data and think that will make sense. No. Many people also consider that when you run a Spark application, the work will be distributed among a group of machines, and eventually the data will come back to the driver. This is not the common case, and if you do it this way, things will break. Okay, so the driver is just for orchestration, and we'll see how. After that, lazy execution is very, very important here. Many data scientists, and I'm not blaming them, they are not aware of this kind of pattern or fact, and their pipelines, they use Spark to build machine learning pipelines, and eventually think it will be very slow because they are not aware about the fact of lazy execution, and we'll have a look on that as well. And Spark is designed to be reliable, meaning that you can be running it on AWS or whatever, and you can be using spot instances, and eventually one of the machines or workers will be taken away from you. Spark is designed to live beyond this fact and continue working fine. So you need to be aware of such fact and how it will impact your pipelines, especially if you are writing to a non-idempotent thing, like a database. We'll have a look on that as well. And we'll have a look on how your input data will impact, or how to understand, I have a CSV or I have a Parquet file, how that will work when you load the data at the first stage of your pipeline. Cool. So first advice here is very, very obvious, and I think many people here are aware of that. Don't collect to the driver. The driver is just for orchestration. If you'd like to have some pipeline and get some metric about your data, like count or whatever, count is a single number, so you can use it. But collecting is meaning like what you have a data frame of 1 billion records, and then you grab everything from all the workers and put it in the memory of the driver. That will eventually make it very, very slow, because you will be consuming the memory, or it will crash it completely, okay? So that's a small example here, kind of a simulated data set, a little bit big one, and I'm doing a collect here at line 3, as you can see, all right? So other than the collect will be taking too much time, like 1.79 minutes, have a look on that spike in the middle. at the second screen, second part of the screen there, the big part of the yellow is increasing since we started to do the collect. This is memory, by the way. The second chart is the memory. When you do a collect, all that data will come into the driver single machine, and it will consume memory. Eventually, the memory, you can consume all the available memory, and eventually your application will break. Or it will also put extra memory on the driver, extra memory load, and it will be very slow. So collect is a very, very bad idea. You can do your job or requirement without really using a collect. You can just write the data or summarize it before you do a collect. The second idea here is lazy execution. If you have a data frame, you pull it from some remote location or multiple locations, and then do a little bit of processing here and there, maybe UDFs or whatever, and you have the data frame as a variable in memory. Then you would like to do a group by on a certain column and another kind of calculation on another column in 2 different steps. If you do it in 2 different steps, the whole DAG will be executed twice. I've seen data scientists pulling data, doing this kind of feature engineering. You have a data frame variable in memory, and then, okay, go do a group by column 1. Go do a sum column 2. And then the DAG will be executed many times because of the lazy execution nature of Spark. So here I'm just simulating a very slow or a little bit of complex or slow process, simulating by using sleep and UDF or whatever. And if I go to the next screenshot, I'm taking the same data frame, doing a group by category, doing an average for one column. You can see that it will take 27 seconds. Again, it's the data frame. Do another group by, but again, it's a different column. It will take another 27 seconds. Why? Because of the lazy execution. It will go and it will need to run the same logic again, even if it needs to grab the data from a very remote location or whatever. So that's lazy execution. You need to be aware of that fact. The solution here, if you'd like to do, if you have done very, very complex calculation and you have some data frame as a variable, try to either cache it if your data is small, or you can persist it to disk if your data is a little bit bigger, like 100 megabytes. So the first cell at the top is just persisting that kind of calculation, and that's why it will take 34 seconds or whatever. After that, I'm doing the same kind of group by queries twice, for different columns. And you can see that both of them are very, very quick, like 3 seconds and 2 seconds. Why? Because the data is already, all that kind of complex calculation and slowness or whatever has been done and persisted somewhere, in memory, on disk, or whatever. So that's the impact of lazy execution. If you have something very, very complex and you would like to use the outcome many times, try to either cache it or persist it. There is the idea of task retry. I mentioned that Spark is running, your Spark query will be divided into a group of stages, and every stage is composed of a different, multiple tasks. Every task is running on one of the cores on a virtual machine. Sometimes tasks can be retried. In many different situations, I mentioned the idea of spot instances being taken away. Sometimes also you can have a network issue somewhere, or a machine having some operating system updates or broken or whatever, and then Spark job will not be failing. It will just take the same piece of work assigned to a certain machine or certain task and send it to another machine. Okay, so certain tasks can be retried. And you need to be aware of that, because if you are writing to a database, for example, and just appending to a table, so sometimes you load your data, do some processing, and the destination will be SQL Server. Okay, so you're appending to a table on SQL Server. If you are not aware about, the implication of task retry, you might be putting duplications in your sink. Okay, some sinks are idempotent; they can accept this kind of or handle such situations. Some of them are not. So sometimes you need to use a library that is supporting idempotent writes. The classic GDBC library from Spark does not. So some other vendors like Microsoft or whatever, they have their own libraries that will support or help you with this kind of ideas. Like if a task fails, your write will not produce bad data. So you can see here, this is just a simulated example using a feature called the speculative execution in Spark. And one of the tasks has failed, and it has been resubmitted on another machine. Okay. So this one is about your input data. So we know that you are collecting data from many sources. Sometimes you can grab them from cloud storage in different formats, CSV, JSON, whatever, Parquet. Sometimes you grab them from database systems and so on. But if you are loading from files, just be aware that not every file format is splittable. The idea here is that let's assume that you have your data coming in a single file, 1 terabyte or 100 gigabyte or whatever. If that file is not splittable, Spark will not be able to distribute it among all the machines and process your data quite fast. So many file formats are splittable. CSV is splittable, and that's why you can see in the next, you can see it here, first part of the screen, there is job number 7. You have 14 tasks, okay? Meaning like Spark can distribute that kind of file reading among 14 cores, okay? Parquet is also splittable. You can see also in the middle part of the screen, job ID 14. We can split that file read operation among 8 tasks. But JZip, for example, is not splittable. So let's assume that for any reason, your upstream, they provide you the source data in JZip format for any reason. You know that that will take too much time to just load the data from disk into Spark memory. And that's why you can see here a job ID number 5 at the bottom is just doing 1/1. 1/1 means I'm also only using a single core on my cluster, which can have like 100 cores. Okay, so that will be very slow. So you can either be aware of it if you are loading small data, no big deal, or otherwise ask your upstream people to provide the data in a different format. And as we are talking about source data, let's talk about some of the very common use cases, which is loading data from Postgres or MySQL or whatever. These are relational databases, which means, think about it, if you are writing an application in whatever programming language and you read data from such applications, you are normally doing it from a single connection, single session, single thread. You cannot really have multiple threads. All of them are running the same query and grabbing data in portions or grabbing chunks together and having a single result set. So if you are loading data from a GDB source, just be aware that it will be a single connection and it will be a single core loading your data if you are loading 100 million records or whatever from a database. So that's why if you do the plain GDBC reader, you will see that usually you will get one task running in the middle of the screen here. There is a Spark history UI. You can see 1/1. And at the bottom of the screen, this is a SQL Server, for example, what they call it, query profiler, showing you the queries that are received from clients of the SQL Server. You will see that, okay, you are loading a single table, you will get select star from that table effectively, okay? All good. But the JDBC reader itself, it has a solution. In case you can do it, you can divide your table into chunks. You can have a single column, like a numeric column. Think about it like customer ID or order ID. Try to find the min and max values in the table. You can do them in another Spark query very fast. And then use something called partitioning. So think about it like this one. You have customers from range ID 1 to million or 100, for example. And then you can instruct Spark, okay, go please do customers from 1 to 10 on one machine, from 11 to 20 on the other machine. And this is like what the idea of partition column and lower bound or upper bound stuff. So that will work. And the major difference here, as you can see, the number of tasks here is 8, not 1, which means Spark will be able to distribute that piece of work and load your data much faster, okay? And the evidence here is that if you run something like SQL Server Profiler, you will see that instead of a single query hitting your SQL Server database, you will find many of them according to the number of partitions you specified. And every one of them will have some sort of where sales order ID is greater than 1 and less than 100, and so on. So for JDBC, just try to make sure that if you are loading a really big amount of data, try to do the read in a partition manner. All right, so this was the first part. I hope it was useful. The second part is about your queries. So it's more about how you are writing your data frame transformations. You know that in Spark we have two concepts, transformations and actions. Transformation is just the logic to take your data and join it, filter it, do this kind of things. Action is collect or count or write the data to a destination. So in many queries, you can be writing your transformation in SQL or Python or whatever, and then eventually they will run on a single core as well for reasons. We'll have a look on some examples. So running on a single core is also a very, very bad problem. We have been doing stuff at major clients, and then if you are running for any reason, sometimes it's due to data nature, a single core query, and then loading like 1 billion records and processing them, it will take forever, or it will even never end. The guys over there, they try to throw as much compute at the problem, like create a cluster with 20 machines, very, very big machines, and thinking that the more hardware you throw at the problem, it will solve it, but it doesn't happen because it will eventually still work on a single core and you'll need to wait, all right? The next one is data types. So you need to be aware about certain impact of certain data types and how that will relate to your output or your queries. We'll have a look. And metadata. Sometimes having some extra data about your tables, like number of records or the distribution of certain values in a certain column, will make a difference for your queries. Let's have a look on one example for a query that will cause your job to run on a single core, which will be extremely slow. So there's something, a window function, I think. Have you used window functions before? Okay, cool. So a window function here at line 9 and 10, you can see we are doing a raw number, which is very famous window function within a certain partition or window of data, doing an order by or whatever. And you can see in the Spark jobs kind of summary of the jobs and tasks and whatever, it's running the stage 133 on 200 tasks. This is one of the magic numbers in Spark. You can tweak it if you want. But this means that when you run this kind of query, which is a raw number and partitioning and stuff, it can be distributed across 200 tasks, okay? Let's have a look on the next query, which is very, very similar, but this time it is messing the partition by clause. Sometimes you would like to do a raw number like an identity column on databases. You think, okay, that's a good idea. Let me load my data and put some identity or index column on top of that. And you'd like to apply it across the whole data set. So 1, 2, 3, 4, 5 until the end of your records. Without having a partition, you will see that at stage 135 at the end of the screen here, you will see that it's running on a single core. Because think about it, you have a group of partitions at different machines, and you would like to apply a raw number globally on all of them. You need to grab everything and put it on a single machine in memory and run some sort of assort order and numbering. So many types of queries, if you do them in a certain way, they will run on a single core. There are solutions to this one, but you don't have to be, you don't have to have a global consecutive ID or index. There is something called monotonically increasing ID, which will create some sort of a unique index as well. Yeah. Plus, it will be much faster. Okay. Void types. So, if you do part of your query doing a select star and adding an extra column of a null value, it will produce something called a void. It's not any data type. So that can happen. I've seen many people adding some null column to their data sets, and then eventually in your target table you will get a void column, which does not mean anything, and it will cause you lots of subsequent problems. So if you need to inject a null, cast it to some specific data type, an integer or string or whatever. And for sure, if you have financial data, try to store it as decimals, because float and double will cause you rounding issues. So you can even try this stuff in JavaScript or many other languages. 0.1 plus 0.1 plus 0.1 floating point or double will cause rounding issues like 0.3, and some stuff, okay? But if you have decimals, you will not get any financial or rounding issues, okay? Metadata. Sometimes when you joining two tables or whatever, if one of the tables is missing metadata like the number of records in the table or whatever, Spark will not have an idea about the volume of that table or input data set, and it will use non-optimal join strategies. One of them is very famous. It's called sort merge join. If you see it in your Spark history, this means that you have a problem and eventually your pipeline is running very, very slow. So the idea here is that I'm doing a join, but one of the tables is missing metadata for reasons. I'll get a sort merge join, but you can provide the metadata by doing some sort of a broadcast, as we see here. If you know that one of your tables is very small, you can just broadcast it. This is some sort of a metadata to Spark. That one of the tables is very small, we can just distribute it everywhere and make our join very, very fast. The other option, you can just persist your data to disk, and eventually you will get metadata from Delta Lake and similar formats. And once you have metadata about your table persisted somewhere, the join will be transformed automatically for you, not you will do anything manual, from a sort merge join to something called broadcast hash join, and it's very, very fast. So a few extra things here. Predicate push down. So sometimes when you are loading data, for example, from a database and you would like to filter your data, potentially you will see that the database is much more efficient in filtering the data at the database side because there are indices, there are many other things. So Spark can help you and push down this kind of filters or predicates to the source. It can be a database, it can be Parquet or whatever. So this is one of the things that you can use out of the box. They will be provided for you. You don't need to do anything really. But sometimes if you write your query in a certain way, you will miss such features. And the other things, we'll talk about UDFs. Many people, because of the simplicity of Python, they will just, okay, I have a string, I'd like to grab maybe the first two characters and do something with them or whatever. Okay, I'll write a UDF because a UDF is a function and you'll just put a decorator, okay? UDFs in Python are very, very slow because think about it, Spark is a Java application behind the scenes, a JVM, and Python or PySpark is just a friendly usability wrapper on top of that. So if you have a UDF in Python, what will happen is that data will go back and forth between the Java process and the Python process, and it will not be in batches. It will be one record at a time, very, very slow. The major idea about Spark and doing such thing is to do things in batches. Sometimes they call it vectorized. Like you have million records, you'll do like what, divide them into 100K, 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 and do everything on 100K directly, not one by one. So UDFs are bad generally. There are some options to make them a little bit faster, which is one of them is called Pandas UDFs. Okay, so we'll have a look quickly on some of the ideas. So this is predict push down very, very quickly. The idea is that, let me show it to you here in the Spark history. And if you write your SQL query and is, for example, loading data from a SQL server, you will see that you have a filter. That filter will be pushed to be executed on the SQL server itself. So in the history here, you'll find something called pushed filters in that black box on the screen, which means that there was a filter that you wrote in your query, but it has been executed on the database. So if you are expecting such behavior to happen, but it doesn't happen, potentially your workload is doing instead of customer ID equals or greater than something, you are doing an additional function on top of customer ID, preventing Spark from applying predicate push down. Okay, let's have a look on a UDF. And maybe the font is not very big here. So I'm using a UDF here. The idea is that I'd like to maybe to grab the first two characters of a certain column and do a group by. If you do it using a UDF, the duration will be very, very, it will take like, I don't know, it's not very clear here, sorry for that, or maybe 29 seconds over there in the middle of the screen, if you do it using a UDF. But if you do it using, at the bottom of the screen, using a plain Spark SQL functions, it will be 5 seconds. So many things you can use with a Spark built-in functions. You don't need to write your own UDFs. The only time I needed to write a UDF was really for decompressing binary data. But other than that, you will find many things. Even on Databricks, you will find stuff for doing encryption and decryption if you'd like to encrypt your data out of the box, so you don't need to write it yourself. Okay, so the other option is to use something called Pandas UDFs. It's a similar idea of a UDF, but it is using pandas, which means that instead of handling one record at a time, you will be sending a series or a data frame, okay, which is somehow a little bit faster. Maybe last thing here is one not very common idea or use case is that Spark, you will have a Spark session or Spark variable, Spark.read, Spark, this kind of things. You can actually create multiple sessions in the same application. Every one of them can have different config values. So sometimes you will have a very, very big cluster running multiple jobs concurrently or even shared among multiple users. And for example, user X would like to have a certain config value of 2, and the other one would like to use 10 because they have different types of workloads. So Spark allows you to create something called a new session, clone it or create spark.new session, which means you will get a new variable. You can use that variable in isolation. Set a different type of shuffle partition number or whatever, such that you will be using your own kind of isolated sandbox environment and not touching anyone else and breaking their application. So the idea is that you'll see that I'm using a Spark shuffle partition once with a value of 23, once with a value of 55. And you can see at the stages in the middle, stage 96, I think, the Spark session here is picking my value in that cloned Spark session to be 23. In the other session, I can see the 55 here because I'm using a cloned Spark session. So that will be very useful, especially if you have cluster with multiple users, or sometimes every one of them will even get his own Spark session. But sometimes in a single Spark application, you can use Python parallelism to run multiple jobs concurrently because you have very big cluster and many of your tables are not really massive. So to make things fast, you can run multiple Spark jobs in parallel from the same driver application. So having this kind of feature will allow you to tweak your Spark session per each type of query if you want to. That's it pretty much. I hope that was useful, and most of the source code you will find it here. You can just some GitHub repo, and happy to take a couple questions. I think we have like 3 minutes.
Thanks, Yousry. Yeah, we'll see. We haven't got much time, but has anyone got an urgent question for Yousry? Or else you can.
2 minutes, yeah.
Yep. All right, we'll just do the one.
Thanks. You talked about UDFs and not to use them.
Yeah.
What do we do? Like if there is a repeated sort of code that we want to use across notebooks or loads, how do we do that?
You mean what are the replacement of UDFs or how to work without UDFs?
Yeah, that's fine.
Okay. So there are many options quickly. One of them is to fall back to Scala if you can, because it will be a little bit faster than Python. The other one is to use Python pandas UDFs because it's vectorized. It can run stuff in parallel. And in many situations, as I mentioned, just have a look on the documentation of Spark SQL functions. You will find lots of functionality that can be done. You can even do it in small increments or batches. Use a certain function to maybe trim string or take a substring, and then you use another function to do a hash or whatever. So you don't have to have a single function doing everything. Sometimes you can compose things together and then eventually get away without using UDFs, and because the performance will be really awful with the UDFs. Okay, yeah.
All right, yeah, we're going to have to get on to the next speaker, but thank you so much, Yousry.
Thank you,
That's
everyone.
awesome.